All right, one of the people that they talk about in the chapter is Bohr. And basically, Bohr is famous for the structure he came up with, what we thought the electron energy levels in the um, outer part of the atom are. So he basically used the letter N to designate specific energy levels or orbits. If you think about the way we picture or imagine atoms, or you see pictures of atoms, it's still kind of the idea of Bohr's idea that basically atoms were restricted to certain energy levels in atoms. They look kind of like the electrons orbit the nucleus. So this is kind of what he's famous for, this, a planetary type model. Each and basically quantum number represents a new principal energy level or an outside ring basically. The nucleus is at the center of the model. That's basically what Bohr came up with. The idea came from the idea or from the study, the fact that he took a bunch of elements in a gas discharge tube, and what happened was, as he sent the light through a prism, it broke into line spectra. So you see it kind of breaking here. You would get a distinct line spectra based on the element, and it had a repeatable characteristic lines. So what eventually happened was he came up with the idea then that he wanted to explain why electrons didn't fall in the nucleus. He wanted to also account for the spectral lines and quantify the atom basically. So what he came up with after looking at spectral lines, for example, if you send white light through, you get a Roy G. Biv. White light gets broken down into all of its visible wavelengths. A line spectra, if you take an element like, for example, hydrogen, if you have it in a tube and you discharge it, it looks pink. The reason it looks pink is it's made of 4 photons of light. One there, one there, one there, and one there. I kind of changed the color with that, but you see it right here. That's why hydrogen always appears pink. And so what Bohr was trying to do is explain why whenever you run electricity through hydrogen, you got the same spectral lines. For example, mercury. If you look down here with mercury, every time you take mercury and you run through a gas discharge tube, you get the same things here. If you look, you get one there, you get one there, a line there, a couple of yellows, an orange, and a red. Strontium, same thing. Get one there, 3 there, one there, 3 there. So each element has its own distinct fingerprint. So what Bohr was trying to do was explain it. He was basically saying that what happened is when you add energy to an electron, it pops up to a certain level, like rungs on a ladder, a certain distance. So like let's say it popped up from here up to here, and then let me change the color on the pen, and it drops back down. So if you pop from here to here, the distance you would fall would release a photon, a purple colored photon, or violet, whatever you want to call it. If you added a certain amount of energy and it fell from energy level, let's say 5, back down, it would release a blue photon of light. So what you would see is a photon of blue light fired out, and so on and so forth. So the same idea is, he basically thought that if the atoms fell at distinct levels or distances, they would release the same photons, and that's what caused the line spectra. So really it's kind of like the idea here is basically you pop up an electron a certain amount of energy. So you go from here up to here, up to here. Anytime you add energy to an electron, it's absorption. So the energy is absorbing energy. When the electron's absorbing energy, then what happens is that the electron will fall back. As it falls, it releases a certain amount of energy. So if it falls from here to here, let's say it releases a blue photon. If you fall from here to there, you release a red photon. If you fall from there all the way down here, you would release a green photon. And that's what causes the different spectral lines, and that's what Bohr came up with. So he was trying to quantify that. So basically, the idea he came up with, a model, accounted for the spectral lines. It made sense. You could actually calculate the radius of a hydrogen atom. Problem was, if you used it on any other atom besides hydrogen, it didn't work. And it didn't explain why energy was quantized. So if you look, he came up with this equation right here. Calculation of energy for a given level. Simple idea. All you do is take B, which is a constant, 2.179 times 10 to the negative 18 joules, goes up on top with a negative sign. And then whatever energy level you're looking for, if it's the first one, obviously that wouldn't be that hard to calculate. It's going to be the same value, but let's say it was the second one, you put 2 here squared over the constant, and you get the value for that energy level. What eventually you get is this equation right here. This is the one we care about, the Bohr equation, to calculate the amount of energy given when an electron either falls or rises. So it could do absorption or emission from electrons in a hydrogen atom. So if you look, you take B, the constant goes right here, 2.179 times 10 to the negative 18th. You have an n value with an I subscript and an n value with an F subscript. And what you do is I is initial and F is final. So if an electron falls from the 5 to the 3, 5 is the initial, so I'd plug in a value here. I'd basically say 1 over 5 squared minus the final value is the third energy level, minus 3 squared over 1, put it in parentheses there, multiply that times 2.179, 79 times 10 to the negative 18th, and you get the value for the change in the energy level. We'll give you a second to do that calculation. When you simplify everything, so you take 5 squared, you're going to get 1 over 25 minus 1 over 9. Do all the math, multiply it. In the end, the answer comes out to be negative 1.550 times 10 to the negative 19th. I'm writing off the thing here, so I'll put it up here. 1.550 negative here times 10 to the negative 19th joules. That's the amount of energy when an electron in a hydrogen atom falls from the 5th level to the 3rd level. If you look at the next problem, their electronic transition from N3 to N8. So the initial value is going to be, go back to the regular equation, initial goes on this side, final goes on this side. So when you go to set it up, it's going to go, now it's absorbing, but it's the same idea. 1 over 3 is the initial squared minus 1 over 8 squared. Set up like this. You get 2.179 times 10 to the, what is it again, negative 18th. Negative 18th. Set it up, and it's a simple calculation. All you have to keep in mind is the initial value goes here, final value goes here. In this case, it's going to be positive value, because whenever you add energy to an electron, it absorbs it. It's going to go up in energy level. And you see that happening whenever electrons go from the 3rd level to the 8th level. It's an absorption of energy, which is going to be a positive sign. In the previous problem, we calculated for the electron falling from one level to the other. Plug it in a simple calculation, and you're good to go.